So Harvard, first talk is by Amir.
Thanks a lot. It's been a real pleasure the last 4 days. So I'm going to talk about very recent work published 2 weeks ago with my grad student Ho, and in collaboration with Ilyas Ofer and Amar Weizmann and Lydia Robert in Paris. And as I just told Herbert, this started looking at cell size and ended up being something else. So the emphasis of this talk will be about multiple replication forks in bacteria. So kind of zooming out, the questions I'm interested in regard regulation at the level of microorganisms. So how do these guys that we just heard talk about, the cellulose, regulate their shape? This is just a family of different bacteria, and you can see a huge diversity in the morphology and relative sizes, but in every family you have very tight control over both shape and of size. So if you're interested in the shape aspect and the mechanical aspect, I'm not going to talk about these works today, but you're welcome to look at them. And today I'm going to focus about how different cellular processes are coordinated within a cell, and in particular growth, DNA replication, and division. And of course, another kind of overarching question is this organism specific, or what are the design principles, and are there general principles? So I'm going to start with, in 1968, with something that we heard about today. So this is a very nice work by Cooper and Helmstetter, where they measured the duration of DNA replication that was just alluded to in the previous talk. And you can see that this is for E. coli, and you see that it's 40 minutes, no matter what the doubling time of the cell is. And then the duration of the D period, the time from termination of DNA replication until division, is another 20 minutes. So it takes always 1 hour from initiation of DNA replication to division, no matter what the growth rate is. And this should bother you at this stage if you haven't seen this before, because you all know that E. coli can double in good condition in 20 minutes. So how the hell do these cells double themselves in 20 minutes when it takes 60 minutes to duplicate their DNA? And the answer to this is multiple replication forks. So basically, a cell has to start duplicating DNA already for its great-grandchildren or great-great-grandchildren. And today, with modern technology, we can fluorescently label origins. This is work from Petra Levine's lab, and you can see that this particular population of cell in a particular growth medium, some cells had 4 origins of replication, and others had 8 origins of replication. So the picture is, if the doubling time is more than 60 minutes, it's simple. You only have a single pair of replication forks going, as we heard, bidirectionally, and with 2 origins of replication. However, if the doubling time is 30 minutes, then you need twice as many, so 2 pairs of replication forks and 4 origins of replication. And you can show from quite simple assumptions that on average, the number of origins should scale exponentially with the ratio of the 60 minutes, the C plus D period, to the doubling time, okay, which doesn't have to be an integer, of course. And so the question I would like to ask today is, how does the cell regulate the number of these multiple replication forks? How does it control to have, on a particular growth rate, 7.5 origins on average? And I'm going to kind of set the stage in the next few slides by making certain assumptions. And one of the assumptions I'm going to make is that growth is exponential at the single cell level. Of course, if you take a colony of cells well-fed, the number of cells always grows exponentially. That's trivial. However, at the single cell level, this was an open question for several decades. And in my mind, one of the most conclusive experiments is from Scott Manalis's lab at MIT, who has very beautiful biophysical methods to weigh cells in a rather sophisticated microfluidic chip. And what he found was that the growth rate is proportional to the mass, and that is consistent with exponential growth at the single cell level, and not consistent with, say, linear growth. So today we believe that E. coli cells, cellulose cells, body yeast, as well as mammalian, all grow exponentially in mass, also at the single cell level. Okay, and there is interesting questions about why this would be so. I'm not going to go into them and just assume for the rest of the talk that growth is exponential at the single cell level with a constant growth rate that appears to be a reasonable approximation for E. coli and body yeast, etc. And this is another example from a work I was involved in where this is a single cell which you make filamentous, and you see that the length on a log scale grows linearly. So again, evidence for exponential growth at the single cell level. A second assumption I'm going to make is that the cells divide symmetrically. So you know that E. coli cells double themselves in length, and then you have the formation of the Fitzy ring, and you get division. And already from work from the 60s, you know that they're very good at dividing symmetrically. So I'm plotting here a histogram of the ratio of the daughter cell to the mother, to the cell before division, and you can see a very tight Gaussian around half, with a standard deviation of about 2%. Okay, and we've heard beautiful talks in this conference about the MINT system that achieves all of this. Again, I'm not going to go into it, I'm just going to assume it as an assumption. This is a modern incarnation of this experiment in microfluidics. You can see that the cells of today are not what they used to be, but they're still pretty good. It's a 4% standard deviation. Okay, so this will have very small effects on all the distributions and correlations I will discuss. So I'm going to assume symmetric division for the rest of this talk. Okay, I'm going to throw more information at you. So this is an experiment even going backwards in time to the 50s by Ilya Schechter. And what you see here is the average size of an salmonella cell, very close relative of E. coli, so nearly equivalent. And you see here the mass, and every point is a different growth medium. So kind of like us, you give them good food, and they grow to be bigger on average. And he found a very quite remarkable quantitative dependence that the average mass of a cell goes as e to the lambda t, so it's exponential. This is a log plot in the growth rate. And the slope of this exponential turned out to be 60 minutes, the same 60 minutes that we had in the Hamster and Cooper C plus D period. Okay? And a decade later, Donachie combined these two observations and said, well, if we know that the average cell size is exponential in the growth rate, we can infer what their size was 60 minutes before division, okay, which is the time of initiation of DNA replication. And simple math will show you that these two assumptions lead to a mass at initiation of DNA replication, which is constant per number of origin. Okay, so again, combining these, you find that there is a critical mass per number of origin at initiation of DNA replication, and that led to the mechanistic picture where DNA replication initiation will occur when you reach a critical mass per number of origins. And I will claim that there is a subtle flaw here because we're using ensemble average measurements to deduce something at the single cell level, which I will show you in the next slide is inconsistent with other observations. A second reservation regarding this work is that it doesn't explain the question I started out with, which is how do you regulate the number of multiple replication forks? You just assume that the cell knows how many origins it needs to have at a given growth rate. And so regarding the discrepancy with a single cell and ensemble average, one issue is correlation. So if this hypothesis is correct, and you're basically thresholding size at initiation of DNA replication, you're basically washing away all the memory of the initial condition. So if you're born small or born large, when you're thresholding something, you're going to get no correlations between, say, the size at birth and the size at division. However, these correlations were reported already back in the 80s, where in a beautiful paper by Koppes, they found that size at initiation and size at division are nearly perfectly correlated. That's not contradictory to anything I said, because if there is a constant duration from initiation to division of 60 minutes and growth is exponential, these two variables just differ by a constant, e to the lambda t, and so they should be very highly correlated, so that's fine. However, they found that the size at birth and size at division has a correlation coefficient of 0.55, certainly different than 0, and so contradictory to this thresholding hypothesis. And so now I'm going to backtrack and show you a rather generic model that will enable us to take this value of correlation and infer what the regulation strategy that the cell is trying to do, okay? And so the idea is the following. I'm assuming that the cell has a deterministic strategy which it's trying to accomplish. So for example, size of division is attempted to be some function of the size of birth. And this function will encapsulate the regulation strategy. So for example, thresholding means this function is constant, while if I grow, a priori you might think that another strategy is just double my initial size, to be born a given size, be newborn, and to try to divide at twice that size. Okay? Now, for any strategy, you can show that the only thing that matters is the derivative of the function at the typical newborn size. And the reason for this is that size distribution in nature are rather narrow, so you can tailor expand around the typical newborn size and only the derivative will matter. The advantage of that is that we can parameterize the strategy not by a full function, but by a single parameter, which I will call alpha, that controls the strength of the strategy. And without going into the details, this is a particularly convenient choice where alpha going from 0 to 1 interpolates between this regime, which turns out to have no size control, where you're trying to just double your size, to the thresholding, which intuitively is clear is the strongest size control possible. So any strategy that you give me, I can tell you which value of alpha it corresponds to by matching the Taylor expansions around the typical newborn size. Okay, so there is nothing arbitrary in this choice. Any model you can map to a particular value of alpha. And as an example, for alpha equals half, the function that I choose is twice the geometric mean of V naught and the size at birth. And by Taylor expansion, you find that that's equivalent to adding a constant to your size at birth. So f of V newborn is V newborn plus a constant. And that has been known in the literature as the incremental model. And I'll get back to this nice work from the 70s later on in the talk. Okay, so for alpha equals half, you're trying to add a constant volume from your size at birth to your size at division. And now we add noise. So of course, this is what the cell is trying to do, and to that is adding some noise. And you can add the noise to the volume or to the time, which makes it a multiplicative noise source effectively. It won't matter for any of the calculations that I'll show you here. There is very weak dependence on the form of the noise. And now the model is exactly solvable. So again, I don't have time to go to the details, but we can close the equations and find what the size distribution is. And we find for time additive noise that the size distribution is log normal, and depending both on a single noise parameter, the noise that I'm adding will determine the width of the size distribution, and alpha, the control parameter. So you can see that you can show that for alpha equals 1, the distribution is the narrowest possible, and for alpha going to 0, you get an infinitely broad distribution. You're losing your size control as alpha goes to 0. You can also solve the time distribution, and you get a Gaussian distribution of generation times. And again, an important point is that it depends on a single noise parameter. So a single noise determines both the size distribution and the time distribution. All right, so kind of this is the math that I need for this. So a single noise added to time, for example, will set the width of the size distribution and the width of the generation time distribution. Okay, and we'll test this in a few slides. And now we can calculate, for example, Pearson correlation coefficients. So remind me that's the expectation values of fluctuations around the mean values normalized by the standard deviation. So they go between -1 and 1, telling us if the variables are correlated, anti-correlated, or independent. And for example, when we correlate the correlation size between a mother-daughter and between a mother and a daughter size, we find that it equals to 1 minus alpha. So again, if alpha is equal to 0, we have terrible size control. The size distribution is very broad, but we have very high correlations. If alpha is 1, we have very tight size control, but the correlations are 0, as we intuitively expected. We're washing away memory of the initial conditions. So now, the value of 0.55 gets a meaning. It suggests alpha of approximately half, which corresponds to this incremental mode where you're adding a constant volume from birth to division. All right, so in collaboration with Lydia Robert, we indeed see that for E. coli cells, kind of low-tech experiments on agarose, you get a very good agreement between the prediction for alpha equals half, V division, the volume at division is correlated with the volume at birth with a slope of 1. And this is also an agreement with beautiful experiments reported in the last year. And we can get the correlation between size and time, and it also agrees beautifully with no fitting parameters. We can calculate the correlation coefficient between size at birth and generation time, which we can show to be -half. This was measured also quite recently. So we get a bunch of correlation coefficients that agree. We can scale the distribution. So the fact that a single noise in the model corresponds to both the size distribution and the time distribution enable us to collapse the size and time distribution. These are the measured ones without any fitting parameters. So for example, a prediction of the model is that the coefficient of the variation of the size distribution divided by that of the time distribution is log of 2, which is about 0.69, and experimentally we get a value of about 0.67. So we get excellent agreement between the experimentally measured correlations and the theoretical one. However, I did not explain the paradox that I started out with. So now I'm going to, after hopefully convincing you that this is a very good model to explain the correlation, that is not the complete picture. And the reason is that we still haven't explained Donaghy's result of the constant mass at initiation. Okay? So I'm now going to get away from this birth-centric model. Even though the model seems generic, it has a very strong assumption that you're born a given volume, and that's what you're trying to do, to, based on that information, try to attempt to grow for a size and division. And I'm going to get away from this birth-centric model and claim that what the cell is actually trying to do is attempt to add a constant volume per origin from initiation of DNA replication to the next initiation event. I didn't know this is going to end up this way, but DNA is kind of jumping in the picture, and I'm claiming now that this is the right way to reconcile this paradox between Donaghy's result and these correlations. So what we show in this recent paper is that if using this assumption, we can explain all the correlation and distribution that I just calculated, that I just showed you, also get Donaghy's result that average mass at initiation is constant per number of origins, and get as a prediction that size depends exponentially on growth rate. So this is not some adaptation in our mind, as it's often viewed in the literature, but just a simple consequence of this regulation strategy. And most importantly, this will regulate the number of multiple replication forks without being put by hand. So this strategy regulates the number of replication forks. And so I probably shouldn't, I should probably skip this calculation, but you can show that if you're trying to add a constant volume from initiation to initiation, a few lines of calculation show that effectively what you get between size at birth and size at division is that size at division is, on average, size at birth plus a constant. So it maps to the incremental model. However, the constant is now growth rate dependent and in an exponential way. And you can easily convince yourself that this constant here must be the average size of the cell. Because if after 1 million generations I added 1 million of these deltas, I have 1 million cells, and this must be the average cell size at birth. So we get for free that all the correlations will be intact, but now we get as a side product that size depends exponentially on the growth rate. And again, the logic is just going through the math of if I'm attempting to add a constant volume between two initiations, backtracking what the correlation between division and birth are. And so these are recent results to show you that, most importantly, the number of multiple replication forks is regulated. So what I'm showing you here is I start in a simulation with the wrong number of origins for that growth condition. So this is the growth conditions where I should have 16 origins on average. I start with 4, and the red curve is a moving average, and you can see that you quickly, after a transient, stabilize to this steady state. So no matter what conditions you start with, you will converge to the right number of origins. This model robustly does that without being putting it by hand, and this is the result at different growth conditions, the average number of origins as a function of the growth rate, giving you this expected exponential dependence, again, as a result of the model of this simple hypothesis, which we term the multiple origins accumulation model, and so it comes as a causal consequence of it. Another prediction that we get is that the number of origins is proportional to size, and this is in agreement with a relatively recent experiment in E. coli and iPoLS, where you just count directly, you measure the number of origins per cell as a function of the cell volume, and you see a roughly linear dependence, again consistent with what we're seeing, but we are claiming this is not some adaptation to the growth condition, but just a consequence of the regulation strategy. And another example of this, okay, so this is one exciting prediction that we get that has not been reported yet, and I'm hoping that in the next few years technology will get there, is the size distribution at initiation of DNA replication. So people currently can measure the size distribution at birth and division, and they see something approximately equal to a log normal distribution. Our prediction based on this model is that we should get a bimodal distribution of size at initiation of DNA replication, where the secondary peak can be either to the right or to the left of the main peak, depending on the growth conditions, and its magnitude depends on the stochasticity. So this side peak is a direct consequence of stochasticity. And so I'm hoping that in the coming years, people will test this by measuring initiation at the single cell level. And another thing that we think we can kind of shed light on is these beautiful experiments by Lenski evolving bacteria over thousands of generations. And these are results from an old paper by him where you see the relative fitness growing over thousands of generations, and you see also cell volume increasing over these generations. And in light of what we're saying, I'm claiming that this is not some adaptation to the new condition, to the conditions over time, but just a simple consequence that we expect volume to be exponentially dependent on the growth rate. So as the growth rate, the fitness evolves, it must be that cell size increases respectively. I'm going to allude to the molecular mechanism. We don't have a molecular mechanism that implements this, but there is a beautiful paper from the 70s that theoretically can implement exactly what we're saying. So it's extremely simple, so I'm just going to spend 1 minute to describe it. You have one protein that is an autorepressor, and under the same promoter, another protein will be the initiator of DNA replication. So as the cell volume grows, we're going to make more of this protein P1 to keep its concentration at constant density. And since they're under the same promoter, the amount of P2 that I will be getting is also proportional to the volume change. Now, if in our picture P2 goes to each origin of replication, by thresholding the copy numbers of P2, if we need 20 copies of P2 to initiate DNA replication, we're exactly going to implement this multiple origins accumulation model, where we add a constant volume per origin of replication. And as it happens, DNA A is a protein that autorepresses, and it has two forms, an ADP and ATP bound form, and you need 20 copies of it in its ATP bound form to initiate DNA replication, after which this form is degraded to the ADP1 form. So we think that DNA A is a strong candidate for actually implementing this strategy that is equivalent to our hypothetical model, this multiple origins accumulation model. And so obviously a lot of molecular work will be done to confirm this or find alternative models. But this is, for me, a proof of principle that this is a simple molecular mechanism that can add a constant volume from initiation to initiation without ever measuring absolute volume. So the remarkable thing is you're adding a constant volume and effectively regulating both multiple replication numbers and size without ever measuring your size at any point in time, which is kind of, for me, counterintuitive. So I'm going to spend the last 3 minutes asking what about other organisms, and there is a famous quote by Monod, anything found to be true of E. coli must also be true of elephants. This is not true in this case. So there is a paper from last year on fission yeast where they measure exactly the same correlation I discussed here, size at division versus size at birth, and the slope is not 1 as we expect in our model, but 0.6, so distinctively different. So fission yeast does not fall into this category. However, there is a paper that I referenced earlier by Jacobs Wagner's group at Yale, showing that this model seems to be relevant for Colobacter, which is a very different kind of bacteria, asymmetric division, etc. And you can see here that delta L, the change of length, is a function of length, and you can see that it's constant. So it's adding a constant increment of volume from birth to division. And again, one take-home message is don't be fooled to think that this is what the cell is trying to do, because you will get exactly the same correlation also if you're adding this increment from DNA replication initiation to DNA replication initiation. So that's a kind of modeling lesson if you want. And in collaboration with the Nama Brokai's lab at Weizmann, we asked what happens for body yeast, which is is now a completely different territory. It's a eukaryote. It divides asymmetrically. So you basically have budding. You grow exponentially, as I mentioned before. And once you bud, all growth goes into the bud rather than the mother cell. Okay? And so these are the correlations that we measure. So these are 5 different growth conditions. And this is size at division versus size at birth. And the red points are taking these clouds of raw data. So every point in this cloud is a cell. And when you build these according to the newborn size, you get these red dots, which are very nice, smooth, linearly dependent. And the black lines in all of these curves are not the best fits to these linear, but all have a slope of 1. So you can see that the data is extremely well consistent with a size at division equals size at birth plus a constant, which is against the dogma in the field of budding yeast, which is a critical size for budding. So this argues strongly against this dogma of critical size for budding. The best fits give you something between 0.91 and 1.1. So it's very consistent with that. You can do the next thing, which is to look at the time between birth and division as a function of the size of birth. And again, when you bin it, you get the red dots, and the black curves are not fits, but they're just this formula, log of 1 plus a constant over V newborn. So it's just these functions that I'm plotting here. There are 0 fitting parameters. We know what delta is. It's just the intercept in the previous plot of the size of division versus size of birth, and we know the growth rate independently. So without any fitting parameters, we can explain the data quantitatively. And again, naively you would say, well, then it seems like budding yeast is adding a constant volume from birth to division, but we can rule that out because the duration of the budded phase, the time from budding to division, is constant and independent of size and birth. So it cannot be that you're trying to add a constant volume from birth to division, because then you won't know when to trigger the budding event, which occurs a constant time before that. And our solution is identical to the one for E. coli. If you're trying to add the constant volume not from birth to division, but from budding to budding, then you get all these correlations, but also explain why the duration of the budded phase is constant. So again, same principles seem to apply both for E. coli and for budding yeast. My kind of main message here was that correlations measured at the single cell level combined with mathematical modeling are very useful, and that we get to this paradigm that a cell attempts to add a constant volume per origin between 2 DNA replication initiation events. And for more details, I refer you to this recent publication and this one unpublished one in the archive. Thank you.
Questions?
You should work on cancer.
So I just looked last night on a nice paper claiming that budding yeast is a good model organism for cancer. So I think it's an interesting direction.
Your proposed model, P1 and P2, is that stable enough, or because it's collective? Any fluctuation on P1, so for example...
So first of all, it's not my model, it's from the 70s.
I know, but you're...
So what they do in that paper is exactly analyze the fluctuations. Okay, so I'm not saying it's the final answer. I think it doesn't. I think a real model should respect the biochemistry of DNA and all the details that we know of it, and that's our goal for the coming years, to come up with such a model. We were starting to collaborate with Mike Lau at MIT on. But I think a molecular model should explain this coefficient of variation from first principle based on, say, number of fluctuations of this initiated protein.
You probably don't want to do the single protein.
Thanks a lot for a very fascinating talk.